Hello, welcome to the second class. Let's start doing exercise 2 that says that three massless perfectly elastic springs A, B, B, C and CD are attached in a horizontal line as shown in the diagram. The ends at A and D are fixed. The objects of mass M are located where the springs join at B and C. The two outer springs A, B and CD have natural lengths A and stiffness K, while BC has a natural length A' and stiffness K'. The distance L between the fixed end points AD is greater than the total natural lengths of the springs. And first of all, they demand that using x1 and x2 as shown in the diagram for the coordinates of the two masses construct the Lagrangian, etc. etc. Okay, I would like to tell you how to get the solution in a different but similar way. Let's see. There are many ways to do this, but there is one that I really like. First of all, we consider a Lagrangian with the usual form T minus B. As in the problem we have two particles in one dimension, then we need x1 and x2 coordinates to describe the system. T is the usual kinetic energy, m over 2 x1 dot square plus m over 2 x2 dot square. And the potential energy due to the springs, we can assure that the form is quadratic. I mean, some constant A, x1 square plus b x2 square plus c x1 plus d x2 plus f x1 x2 plus g. And as you know, the Euler-Lagrange equations read like this. I've introduced this notation. With this notation I mean x1 and x2 organized in a nice vector. Then partial L with respect to x vector is equal to partial L with respect to x1 and x2. And of course, if we develop this expression, we obtain 2ax1 plus c plus f x2, and the other component is 2bx2 plus d plus f x1. But we can write this expression matrix form like this: 2a f f 2b times x1 x2 plus c d. Or in a simpler notation, partial L with respect to x vector equals a sum matrix M, this matrix, x vector plus q, for example. We can call q to this vector. And then, if we consider now the derivative with respect to the velocities, we obtain m x1 dot m x2 dot, and if we now apply the time derivative of this vector, we obtain, of course, another dot here and here. The Lagrange equations say that m x1 dot dot m x2 dot dot equals matrix M x vector plus q vector. Or we can call this m x vector dot dot equals m x plus q. Okay, this is nothing more than usual equations but organized in a matrix form. Up to here nothing is new, but the nice thing happens when we think or we see that this matrix is symmetric. You can see this because of this f and this f. Then this symmetry implies that m can be diagonalized, namely, if we multiply m both sides by u, mu inverse, we can obtain a diagonal matrix. U is an unitary or orthogonal matrix. Orthogonal if we are working with real numbers, and unitary if we are working with complex numbers. If we isolate m, multiplying to the left by u inverse, then this u cancels, and if you multiply to the right by u, then you isolate m. And now, if we substitute into the Euler-Lagrange equations and define ux as a y vector, then x vector is equal to u inverse y. And of course, due to this matrix is constant, then if you derive twice, u inverse remains constant times the second derivative in y. And then substituting here, we have m u inverse y dot dot equals u inverse lambda y plus q. Let's multiply this equation by u to the left. Then if we multiply in this direction, here and here, then this u with this u is the identity times y dot dot. The same thing happens here, lambda y plus u times q. Let's define capital Q as u times q vector. And the nice thing is that now this matrix is diagonal. Lambda 1, 0, 0, lambda 2. And we have got two decoupled equations, namely my1 dot dot equals lambda 1 y1 plus q1, and the same thing but with 2. Now we know that this type of equation, because it's a displaced harmonic oscillator, if we set the acceleration equals 0 to find the equilibrium position, then we find that is minus q1 divided by lambda 1. This is the equilibrium position, plus some constant a, for example, times cosine omega t plus initial phase. And that omega is the usual. In the usual harmonic oscillator is k over m square root. But in this case, we have lambda instead of minus k. And then we substitute minus lambda 1 over m. Let's put this expression here, minus lambda 1 over m square root t plus. And voila, because now we can write the same expression but with 2 here. And here another constant, cosine square root minus lambda 2 over m t. Sorry, there is... well, let me put 1 here and 1 here, a2 here, two different constants. And then we have got the solution. Now let's summarize everything we've done. We have a Lagrangian equals t minus b to Cartesian coordinates, v quadratic, and if we perform the partial derivative of L with respect to x vector, we call this matrix M x plus q vector. This is possible because b is quadratic. On the other hand, we have dt of partial L partial x dot equals m x vector dot dot. We've defined lambda as diagonal matrix obtained by multiplying an orthogonal matrix U times M times U inverse. We call lambda 1, lambda 2 the eigenvalues. Also we've defined Y as Ux and capital Q as UQ. And the solution in Y coordinates is Y1 minus Q1 divided by lambda 1 plus some constant A1 cosine minus lambda 1 over M square root t plus phi1, and the same thing but with 2. So in order to obtain x coordinates, the solution of the x coordinates, we only just to isolate from here, and is nothing more than the inverse of u times this vector, and this is the solution. Let's calculate in our particular example the exercise. Let's write the potential energy. This string is k over 2 x1 minus its natural length a square plus now this spring k prime over 2 x2 minus x1 minus the natural length, that is a prime square, plus the whole thing L minus x2 minus its natural length a again, and this is k over 2 square. Let's compute now partial derivative with respect x1 equals k x1 minus a, and this is because of that sign, this is minus k prime x2 minus x1 minus a prime. That's it. Let's join x1 k plus k prime x1 and 2 is a minus k prime x2 plus minus k a plus k prime a prime. Okay, let's change the sign because we need the force. Sorry, we've calculated the partial derivative of the potential, but if we change the sign, minus plus minus plus plus minus, we then obtain what we want. Let's compute the partial derivative of the potential with respect x2 equals k prime x2 minus x1 minus a prime, okay, minus k L minus x2 minus a, and let's change the sign and we obtain then k prime x1 minus k plus k prime x2 plus k prime a prime plus kl minus a. Let's express these equations in matrix form. M will be equal to minus k minus k prime, k prime, k prime, and minus k minus k prime, and q will be this and this, ka minus k prime a prime, k prime a prime plus kl minus a. Great, we're done. Okay. Now, in order to obtain lambda and u, we need to diagonalize this matrix. If you do it, you'll obtain lambda 1 equals minus k, eigenvector 1, 1. Let me normalize this vector, 1 over square root of 2, here also, and lambda 2 equals minus k minus 2k prime, almost the same vector, but with a minus sign here. And then automatically we have u inverse, because this is nothing more than the first vector and the second vector. Notice that in order to this be correct, you must normalize the vectors. Let's calculate Q, capital Q. Capital Q is UQ. Then, let's write U, the inverse of this matrix, but this matrix is orthogonal, and then the inverse of an orthogonal matrix is just U transposed. And then we only must change the sign, this sign, to here. Okay, if you do this operation, U times Q, you obtain KL divided by square root of 2, square root 2 k prime a prime minus a k plus kl over 2, and that's it, because we have now the solution. The solution is here. We copy that and paste here. Let me see, lambda 1 and lambda 2. Okay, then we will have, this is Q1 and this is Q2. We now have, let's see, minus with this minus is plus, then this k with this k cancels, and then we obtain L over square root of 2 plus a1 cosine all this. And then y2 is minus with this minus cancels, and then we obtain square root of 2 k prime I prime minus ak plus kl over 2 divided by k plus 2k prime plus plus a2 cosine blah blah blah. Let me draw a square, yellow square, and here pink square, blue square. Okay, now x1 and x2 will be equal to u inverse times, let me make some space, this and this, maybe this parenthesis must be longer, plus a1 cosine yellow square plus and the other term. If you multiply this matrix times this vector, you will obtain L k prime minus k prime a prime plus ak over k plus 2k prime and L k prime plus k prime a prime minus a k plus kl divided by k plus 2k prime, and this matrix times this vector is 1 over square root of 2 a1 cosine yellow square a1 cosine yellow square minus a2 cosine blue square, and the same thing but with plus here. The yellow square is, remember this, let me copy all this, it's easier to delete this thing, and this is the yellow square and this is the blue. Remember lambda 1 is equal to minus k and lambda 2 is minus k minus 2k prime, and then the normal frequencies are k over m square root and lambda 2 equals k plus 2k prime over m. And you see now another interesting thing, that is this vector is just the equilibrium position. Okay, let's continue with exercise 5. A bit slides along a smooth wire bend in the shape of a parabola z equals zr square. The bit rotates in a circle of radius r when the wire is rotating about its vertical symmetry axis with angular velocity omega. Find the value of c. Here it's important to notice that we are not referring to a paraboloid but rather to a parabola. Here you have a little animation to show explicitly what I mean. It's convenient to express the variables of the system in cylindrical coordinates, namely r, theta, and z. The change of variable, as you know, is. Here the constraints tell us that the particle, which is here, for example, in a certain instant of time, has a restriction in its angular velocity. I mean, theta dot equals omega equals constant. And the radius r depends on time. But it must satisfy z equals c r of t squared. To obtain the Lagrangian, we need, as you know, kinetic energy and potential energy. Let's start with kinetic energy and let's compute x dot, y dot, and z dot. X dot is equal to time derivative of this expression, and then we compute r dot cosine theta minus r sine theta times theta dot, but theta dot is equal to omega. Let's write omega in this side to avoid later confusions. Let's compute y dot. It's equal to r dot sine theta plus r, and for the same reason we put omega here. But we can do an extra thing. Because of that, we know theta is omega t plus a constant. Let's put this constant equal to 0 for simplicity, and then omega is omega t. Let's compute z dot equals to, looking at this expression, we see that this is 2c r times r dot. Let's now compute x dot square plus y dot square plus z dot square equals to r dot cosine minus r omega sine square plus r dot sine plus r omega cosine square plus 4c square r dot square cosine square plus r square omega square sine square minus 2r dot r omega cosine sine plus r2 square sine square plus r square omega square cosine square plus 2r dot r omega cosine sine plus 4c square r dot square. And then we can cancel out this term with this term. And let's factor out this expression plus this expression. Cosine square plus sine square is equal to 1. And then we obtain r dot square. Okay. Let's see this term and this term. For the same reason, we obtain r square omega square. And let's see, the remaining term is 4c square r dot square. The good news is that in this expression, we have introduced the constraints, this constraint and this other constraint. Okay, let's delete the constraints, also this and this. Let's store these expressions just in case. What we're going to do now is write down the kinetic energy, which is nothing more than m divided by 2 times this green expression, of course with parentheses. Let's store the kinetic energy in here. Now is the turn of potential energy. Here we only have gravity, will be m, g, z, where z is the distance between this point and the floor. But if we use this constraint, this expression becomes m, g, c, r squared. And voila, we have the Lagrangian of the problem, that is T minus potential energy, namely this minus this. Now we can forget about all the previous equations. And here we have our final Lagrangian, which contains all the information we need to solve the problem. Now the question is, what about of this phrase? Is this a constraint? I mean, is R equals capital R a constraint? And it's not a constraint, because if we set R equals R for the beginning, then the picture is like that, and a particle moving in this circle. And the Lagrangian will be m over 2 r squared, because this must be 0, r square omega square plus 0 because this r dot minus mg c r square. Then we will obtain a circular motion. R equals capital R is not a constraint in general. What we are wondering if it is possible for the particle to have an equilibrium motion that consists in R equals capital R as equilibrium. The way in which we'll investigate this question is from the equations of motion, but not at the level of the Lagrangian. This is an important issue. Okay, let's now compute the Euler-Lagrange equations. The three Euler-Lagrange equations, each equation for each variable, but this variable theta doesn't appear in the Lagrangian and z either. The only variable which appear in the Lagrangian is r, and then these two equations are useless. Okay, let's compute the first derivative is equal to m over 2 2r omega square plus 8c square r dot square minus 2mgc square r. Let's compute the derivative with respect to r dot equals m2 2r dot plus 8c square r dot minus 0. Let's compute now the derivative with respect to t of this expression. It's equal to m over 2 2r dot plus 8c square, and first we have 2r dot times r dot plus r square r dot. Let's join these expressions together. First term minus the second term equals 0. We can cancel out m. Let's introduce 1/2 into here. 2 over 2 is 1, 4. The same thing here. This cancels out 4, and this minus here and here. This r dot is square. And now we have the equation of motion, and now we can wonder if is there a solution in which r equals capital R equals constant, what is equivalent to r dot equals r dot equals 0. We can cancel out this expression, this, and all these expressions because of these two dots, this and this. And we finally obtain and this is r capital R, I mean r omega square minus 2gc r square, capital R, and nothing more. We can delete r capital R here and here. If we isolate c, we obtain omega square divided by 2g. And this is the final result. Well, nothing so far. Today's class is finished. Thank you very much for watching the video, and goodbye.